For more than 100 years, modern physics has relied on a comforting idea. Electrons may be strange, but they can still be treated like tiny particles moving through a material. They might behave like waves, they might spread out or interfere. But at the end of the day, physicists assumed electrons still had a position, a velocity, and a path. Now that picture has finally broken. Scientists have discovered a material where electrons no longer behave like particles at all, and yet the fundamental laws of physics remain intact. This discovery comes from researchers at the Vienna University of Technology who studied a rare quantum material composed of cerium, ruthenium, and tin. When cooled to temperatures just above absolute zero, the electrons inside this compound enter an extreme quantum state. In this state, electrons lose their individuality. They don't travel like tiny bullets. They don't follow well-defined paths. They exist as a highly entangled collective quantum system. In most materials, such behavior would make predictions impossible. Many of our most successful equations rely on the idea of particle-like motion. Without it, theory should fall apart. But something remarkable happened instead. The material began to exhibit topological behavior. Topological states are among the most fascinating discoveries in modern physics. They are patterns in the electronic structure that remain stable even when a material is bent, disturbed, or filled with imperfections. These states allow currents to flow in protected ways and are considered essential for next-generation electronics and quantum technologies. Until now, topological materials were believed to depend on electrons behaving at least somewhat like particles. This experiment proves that assumption was wrong. The researchers observed a phenomenon known as the spontaneous Hall effect. Normally, this effect only appears when a magnetic field is applied, forcing moving charges to curve sideways. Here, no magnetic field was present. The effect emerged naturally from the material itself. This was the key signal that topology was arising not from particle motion, but from deep quantum interactions. The electrons weren't acting independently. They were behaving as one coherent system governed by collective rules. This places the material in a new class called an emergent topological semimetal, driven by quantum criticality rather than conventional electron dynamics. Why does this matter? Because it dramatically expands the search for useful quantum materials. Scientists are no longer restricted to clean, orderly systems. Even materials once thought too chaotic or complex may host stable and powerful quantum states. This discovery suggests that order can emerge from disorder, and that robustness doesn't always require simplicity. When electrons stop behaving like particles, physics doesn't fail. It reveals a deeper layer of reality. And in that layer, the future of quantum technology may already be waiting.